Hi everyone. In this video, I want to talk about the definition of work, what energy is, and talk about the way you can use it with gravity specifically as an example. And we'll talk about this in class, but when we're talking about energy, I think the really important point to emphasize is that energy is a useful abstraction, and I have that with stars right here as an interpretive point that's really, really important. So when we're talking about work, which is a way of calculating how much energy is converted from one form into another, and when we're talking about energy conceptually, the reason why we're talking about those things is because they are useful, not because they're obvious or because they're intuitive or because they're real physical things. So let me write that down. Work is a quantity that we're going to work with that's defined because it's useful. And that's really the only reason. It's not used because it's easy to understand or obvious or intuitive. I think this is really important. If you search around and look for people talking about energy, and they start telling you that energy is this thing that exists in the world, and like things have different forms of energy that they have, then that's kind of true, but it really skirts around the main conceptual underpinnings of energy as a concept. Work and energy conceptually are just mathematical abstractions. They're a way of writing things down quantitatively that enable us to think about the world in a completely different way. And I think that at the end of this video, I'll talk about the way that this might help reorganize our thinking. For right now, I just want to define what work is and talk about its relationship to energy. So work is defined as an expression that kind of looks like this. You take a force, you take a displacement, and you take the cosine of the angle between those two things. And you multiply them all together, you get the work done in some process. So what does that actually look like? So if I have a picture, here's a box, and maybe the box is being pushed along a horizontal floor, maybe. And there's a force applied to it that looks like this. So, and that force makes, let's say, some angle relative to the horizontal. And then the box is pushed for some distance until it gets to maybe this spot or here. So the displacement traveled by the box in this process is delta x. Then I'm calculating the work done by this force F in this process as the magnitude of that force times the displacement traveled while that force was being applied in this process times the cosine of the angle between the displacement and the force. So that is, the displacement vector really points this way. So I'm making a little angle where from sort of the tail of the displacement vector, or with the tail of the displacement vector and the tail of the force vector, and the angle between those two things is theta, the theta we're concerning, that concerns us. So physically, what does that mean? It means that if I apply a force in the direction of motion of something, that force is doing work. So if you think about what cosine theta means, if I take a triangle, if I turn this force vector into components. I've got two components. I've got F sine theta, which goes up and down here, and I've got F cos theta, which goes horizontally. F cos theta is the part of the force that points in the direction of displacement for this problem. And so when I'm calculating the work, another way to conceptualize the work is the force in the direction of delta x times delta x. So really that's putting F and cos theta together here and saying that F cos theta represents the force that's pushing whatever our object is, in this case a box, the force that's pushing our box in the direction that the box is moving. You'll notice that in this problem, there's almost certainly other forces that I haven't really considered. So if I thought about other forces here, I could probably think about gravity, and I could think about normal force. And let's ignore friction for now. But in this problem, normal force and gravity do no work. Why is that? So if I denote these by the work done by gravity, let's say, that's going to be equal to the force, which is mg, times the displacement, which is delta x, times the cosine of the angle between gravity and the displacement, times cosine of the angle. So what's the angle? Well, if I say the displacement is going horizontally to the right and mg is going down, the angle between them is 90. So the cosine of 90 represents cosine of the angle between the displacement and gravity. Cosine of 90 is 0. The way to conceptually think about that is gravity does not point in the direction of motion at all. This thing is moving horizontally, so gravity doesn't do work. So what this means is that gravity doesn't really affect the motion at all. And we'll interpret that more in a minute. But the same thing's true for the normal force. So the work done by the normal force times delta x times cosine of the angle between displacement and the normal force. So that's also 90 because displacement goes horizontally and normal force goes vertically. So cosine of 90, that's 0. So in the problem that we have here for ignoring friction, the only force that actually does work is this force F. And if we had numbers, we could plug in numbers. But basically, there's some value for the work done by F and the work done by gravity, and normal force is 0. That means that the big picture way to step back here is F is the force that changes the motion of the box. And it's the only force that does that in this problem. So we would expect that if we think about it from a kinematics and Newton's laws perspective, when you apply this force F, really what you're doing is accelerating the box. So you apply a force F, it accelerates the box to the right. And as it accelerates, it speeds up. So there's two different ways to say what this force F is doing. We can say that force F accelerates the box and speeds it up to the right. Or we can say that that force F does work on the box, because saying that is equivalent to the first thing. If I say force F does work on the box, then that's equivalent to force F is speeding the box up in this case. So force F, we would say, does work on the box. There's a force being applied in the direction of motion. It's doing work on the box. This means that the box speeds up. Okay. the way to quantify a statement like that is to write down something called the work energy theorem. This is arguably the most important thing in physics. So I'm going to put some more stars by it. The work energy theorem says if you take all of the forces on an object and you add them all up and you calculate the work done by all those forces in some process, and I'll call that the net work. So this would be the work done by the net force on an object. That's equal to the change in this quantity called kinetic energy for an object. So let me define these things. So the net work is the work done by net force on a system or an object, on a system, I'll say. And the change in kinetic energy sounds fancy, but it's really just change in kinetic energy is equal to 1/2 mv final squared minus 1/2 mv initial squared. So work is this thing that's done over some displacement. So in our box example above, we start with some velocity. The box has some velocity. We apply this force F. Part of that force accelerates the box to the right, so it speeds up. So the work done by our force accelerates the box and changes its velocity. So the way we would write that down here is we would say the net work done on the box is, so this is for our box now. The net work, we summed up all the work, or we looked at the work done by all the different forces on the box. For gravity and normal force, it's 0 because they're perpendicular to the direction that the box is actually going. For the force F, that force is F times the displacement times cos theta. That's the total work done on the box. And that has to be equal to 1/2 mass of the box times whatever the final velocity of the box is, minus 1/2 the mass of the box times the initial velocity of the box squared. This is extremely powerful. It says that if you can tally up the works done on something, you can calculate the way the motion of that thing changes. It's a different way of conceptualizing kinematics, the way that forces cause motion. Conceptually, it's different. At the beginning here, it might not seem that different, but it is really, really different because there's lots of ways of representing work done by forces, and we'll talk about that later. But the basic premise here is if you can calculate works, you can keep track of what forces are doing and figure out how the motion of an object changes. You'll notice that this equation here doesn't have time in it explicitly. There's all we care about here are the starting and ending points. This is just a start point for velocity. This is an end point for velocity. That's pretty nice. So let's look at a specific example where we plug in numbers. Okay, so let's say I take my box example and I've got that force that I'm applying, maybe that's 10 newtons. And this angle, let's say that angle is 30 degrees, let's say. And it goes 5 meters before we consider what's happening to the box. So we want to know if the box starts at rest, what's the final velocity of the box? And do I need a mass? I guess I guess we can give a mass. So let's say the mass is 2 kilograms. So what's the final velocity of the box? So we argued that the work done here, the net work done by all the forces, is equal to F times the displacement times cosine theta. So that's 10 times displacement is 5 times cosine of 30. And that gets you something. And that should be equal to the change in kinetic energy. So that is 1/2 times mv final squared minus 1/2 mv initial squared. The initial kinetic energy, this term, is 0 because there's no initial energy. So we're really just calculating the final. So 1/2 times the mass is 2 times v final squared. And we're looking for v final squared. So now we can set these things equal 10 times 5 times cosine 30 equals v final squared. So that's a number. That's some number. So that's 50 cos 30 square root. That's something. That's how you can use this. This is a problem that certainly you could do with force analysis and kinematics. You could figure out what the net force is. The net force would be 10 cos 30 to the right. You could figure out what the acceleration was and then calculate how, the velocity after the box had traveled 5 meters. In this simple example, there's not too much of a difference, but this is just a way of introducing the mechanics of how you would use work to actually solve problems. Okay, so I think I'll leave it there. The video is getting a little bit long already. I'll save the gravity stuff for a separate video, and we'll talk more about this in class. This is conceptually very challenging. The mechanics of solving these problems are doable once you get the hang of it, but the conceptual part is really challenging here, and we'll keep going forward with interpretation and talking about work and energy in class. And I will see you all later. Bye.